Question 5 is about blood pressure. A research team conducts a randomized controlled experiment to evaluate a blood pressure treatment. They randomly assign 300 patients to the treatment group, or Group A, and 200 to the control group, or Group B. At the end of the experiment, they measure each patient's blood pressure. They want to test the claim that the treatment decreases blood pressure. Their null hypothesis states that there is no difference between the distribution of blood pressure between the two groups, and any observed difference is due to chance. As their test statistic, they decide to use the difference between the average blood pressures of Group A and Group B, which is the average of Group A minus the average of Group B. The research team asks for your help in simulating under the null hypothesis, so they give you the table of data containing 500 rows, one for each patient. It has just one column, labeled BP for blood pressure, which contains a numerical measure of blood pressure in millimeters of mercury. It doesn't have any labels, so you don't know who is assigned to which group. So part A. You find that the mean of the patient's measurements is 120, the median is 110, and the SD is 20. Which of the following must be true? So the first option is about 50% of the patients have measurements below 110. And this is true by the definition of the median. So the median is the point where it divides the data set in half, where half are above that number and half are below. So by definition, this is true. Okay. So the second thing is that about 95% of the patients have measurements between 180 and 160. So notice that you can look at 80 and 160 as the mean of 120 plus or minus 2 SDs. And that'll give you 80 and 160. So this would be true only if we knew that the distribution of the measurements was normal. We don't know that, and in this case we actually know that the distribution is not normal. And the reason we know that is because the median and the mean are not the same. So this is only true of a normally distributed curve, which we don't have. So this is not true. The third option is that 75% or more of the patients have measurements between 80 and 160. So this one is actually true. And the reason why we know it's true is by Chebyshev's inequality. So what that says is that for any distribution, it doesn't matter what it looks like. It's just literally any distribution. We know that at least 1 minus 1 over z squared of the data are within ZSDs. So in this case, we're looking at 2 SDs away. So it's greater than or equal to 1 minus 1 over 2 squared. So 1 minus 1/4, which is 3/4, or 75%. So we know by Chebyshev's inequality that at least 75% of the data are within 2 standard deviations of the mean, which is exactly what this option says. Okay. The fourth option is that the blood pressure measurements have at least one outlier. We do not know this for sure. There could be a bunch, there could be none, but just by knowing the mean, median, and SD, we can't say anything about that. The last one is, if we converted the measurements to standard units, the median would be equal to the mean. And no, that this would not be true. Because in standard units, we know that the mean is equal to 0, but because we have a skewed distribution where the mean and median are not equal, the distribution of the standard unit calculations would not be normal, so the median would not necessarily be 0. So our answer is this option and this one. Okay, part B. fill in the blanks in the code so that the last line evaluates to one value of the test statistic simulated under the null hypothesis. So the question we want to know here is, what kind of hypothesis test are we doing? And you can think about that for a second, but the answer is that we're doing an A/B test. And we know that for a few reasons. The first is that the question literally tells us we have a group A and a group B. So that's a pretty big hint, right? The second thing is that we are testing, let's see. The other thing that we know is that we don't know which group people were assigned to, which is important for an A/B test, because when we're simulating under the null, we just want to shuffle all the labels and then randomly assign people to one of two groups. Okay, so shuffled, this name is pretty critical in telling us that this line should just shuffle the labels. So data.sample, and then sample can take in two arguments, with replacement equals true or false, and then it can also take in a sample size. So we're not going to give it a sample size, because if we don't, it'll just shuffle everything, and that's what we want. And so then we want to know, do we want to shuffle with or without replacement? So in this case, we want to shuffle without, because we want each data point to still be in the set, just in a different order. So this should just be with replacement equals false. Okay, so now it's telling us we want to make two tables. Specifically, one that gives the A group and one that gives the B group. Okay, so we want to say shuffled, and then so it wants us to take a subset of the shuffled table, which we just made here. So the function that we can use to get a certain number of rows out of the table is take. So shuffle.take, and then so the question says that group A should have 300 people in it. So the easiest way to do this is just take the first 300 rows. And we can do that by saying np.arrange of 300, because it'll take rows 0 through 299, which are the first 300 rows of the table. Now, shuffled B group is just the rest of them, right? So, again, we call take right here, and then this is going to be np.arrange, and we want to start at index 300, and we want to go all the way to the end. And since there's 500 rows in the table, we write 500 here. Okay, so now we have two averages. So mean A equals np.average of something, and what we want here is the blood pressure column from the A table. So we can say shuffled A dot column of BP. Notice that we can't just feed in the table, because np.average works on an array, not a table itself. Then mean B should be shuffled B dot column blood pressure. So the similar thing. Okay, so now the last thing is our test statistic, and the question says it wants our test statistic to be the mean of A minus the mean of B. And so we have those two variables right here, so we can just say mean A minus mean B. And we'd be done with this part. Okay, part C. In part A above, why do we shuffle the data? Choose all that apply. So this is a question that goes into a little bit of the theory behind A/B testing. So the options are, we want to randomize treatment and control to establish causation. So this is not true in this case. Our experiment wants to randomize treatment and control to establish causation. That's true. But our A/B test here is only to simulate a bunch of times under the null hypothesis. So this is not true. The second option is that we want to remove all possibilities of non-random selection. So this also is not why we shuffle the data. That's just like by definition of A/B testing. The third is that under the null hypothesis, the label of being in group A or group B doesn't matter. And this is true because remember when we're A/B testing, we're answering the fundamental question, do these two pieces of data come from the same distribution? So if they do come from the same distribution, then it doesn't matter which group they're in because they come from the same place. So this is a correct answer. Lastly, we want to simulate two groups of people whose expected blood pressure is identical under the null. And this is also true because in this experiment, they said their null hypothesis is that there is no difference between group A and group B's blood pressure. So the correct answer is these two. Part D. Suppose we repeat the procedure 10,000 times and plot a histogram of simulated test statistics. Assume the histogram shows all the simulated values. Which of the following are valid conclusions from this histogram and from the information above? Choose all those that apply. Okay, so the first is that the drug has no effect on blood pressure. We do not know this because this histogram right here is only simulating under the null. Since we are not given an observed test statistic from the experiment, we can't say this for sure. Okay. Okay, the second one is because this histogram is bell-shaped, 99.7% of the simulated values must be between -3 and 3. So this is not true either. This would only be true if the standard deviation was 1, because by the normal distribution, we know that 99% of 99.7% of simulated values should be between -3 and 3 SDs away, but we don't know what the SD is here, so we do not know this. Okay. The third one is, if the p-value cutoff is 0.05 and the observed test statistic is -3.5, then we should conclude the data are more consistent with the alternative hypothesis. So let's draw where 3.5 is on our histogram. Let's draw it in green or blue. No, let's do it in green. 3.5 is around here. So we want data more extreme than the observed value, so we would go to the left. So we want to know basically how much data is here to the left of our value. And the answer is not very much. So if we take this entire bar right here, I'll draw it in red. If we take this whole bar, which by the way includes both data to the left of our green bar and to the right of it. But let's just for now assume that all the data is bunched up on this side of it. So the area of the histogram is the width times the height. So our width is 1, right? 4 to 3 is 1. And then our height is about 2.5%. So 1 times 2.5% is about 0.025. So we can say right here, let's see, we can say P is about 0.025. And this is less than the 0.05 cutoff value. And when the p-value is less than the cutoff, what do? We reject the null. And we would say that the data is more consistent with the alternative. So this one is a valid conclusion. Okay. The fourth option is if the p-value cutoff is 0.01 and the observed test statistic is -0.2 or -2.5, then we should conclude the data are more consistent with the null. So let's again draw us a line where -2.5 is, and that's going to be right here. So all the data to the left of this line is more extreme. And this time we don't really need to bother calculating how much area is in this bar, because it's very clearly more than 1% of all the data. So we would say that in this one, P is greater than 0.01, and that means do not reject the null. And so we would say that in this case, the data are more consistent with the null hypothesis. So this would be a valid conclusion right here. So our answer is these two. Okay, part E. Suppose the research team now tells you the observed test statistic was -15. Which conclusions are the data consistent with? So now, our line is like way back here, right? Because -6, -15 is way to the right of the graph. So our p-value is pretty clearly 0, because there's like no way there's more extreme data than right here. So if the p-value is 0, then which of the following are valid conclusions? So the first is that the difference in blood pressure between the two groups is not due to chance alone. That is valid. Then the second one is that the treatment has a positive association with blood pressure. So this one is not true, because the treatment actually decreases blood pressure, which would make it a negative association. So it's not positive, it's negative. The third is that the treatment has an effect on blood pressure. And that is yes, because we can prove that it has an effect because we did our randomized controlled experiment. So yes, we can say because there is a difference, there is an effect, like a causal effect. D is that the treatment lowers blood pressure, and this is also a valid conclusion because we've proven that -15 means that there's like a 15% or a 15 difference in blood pressure when you use the treatment. And then the last one is that there isn't enough information. I mean, there is. We just have like 3 right here, so this is not correct. So these are our correct answers.